I still have this wonderful combination of jet lag and weird dreams. I dreamt last night I was going to Boston and I was building a deck, like like something you stand on. Why my mind decided to do that? But jet lag. Anyways, well, a student emailed me today and said she's going to miss a lecture, and I said, "Oh, it's too bad. This is one of my best lectures." Not that all my other lectures are horrible, but this is a good one because you'll do a lot of work in this one. But does anybody have any questions about anything before we start? Okay, so where we left off is on balancing chemical equations and the information in them. So this chemical equation here, methane, CH4 plus 2 O2 oxygens makes carbon dioxide and water. And the chemical equation tells you what type of atom you have in each of the compounds. I guess this is an element, but what each of the molecules, and how many of them are in each molecule, how many of each molecule you have, and then what states they are in. So lots of information. So we're going to start off by learning how to balance chemical equations. And this one is balanced. This one is balanced. You have on the left side, you have one carbon. On the right side, you have one carbon. On the left side, the reactant side, you have 4 oxygens, right? 1, 2, 3, 4. And this also you have 4. 1, 2, 3, 4. Same with hydrogens. 4 hydrogens here, 4 hydrogens there. So when you balance chemical equations, you have to have the same number of each type of atom on both sides. And so let's do this for this equation here. So butane, C4H10 plus oxygen makes carbon dioxide and water. So the way that you balance an equation, start off with an element. I'm going to pick carbon just because it's only in one species. You can pick any element you want. So 4 carbons here, then 4 carbons there. So notice I put a 4 in front of CO2, so now we've balanced the carbons. Let's talk about what I can't do. I can't do this. I can't put a 4 underneath the carbon like I just did there. So if you see I put a 4 underneath there, you cannot do that because now you have a new molecule. So you have a new compound. So that is not proper. You have to put 1 in front of the compound itself. So 4 carbons. So let's balance hydrogens. There are 10 hydrogens on the left, so I need 10 on the right. And how do I get 10 on the right? I put a 5 here, because 2 times 5, H2, 2 times those 5, will give me 10. And if you haven't noticed, there's going to be a problem because there's an odd number of oxygens. So since there's an odd number of oxygens, I know I'm going to have to double it. So you can do it in one of 2 ways. You can just go ahead and double it right now, or you can just keep on carrying through the fractions. I tend to just carry through the fractions. So what I mean by this, how many oxygens do I have? So for oxygens, I'll change colors. I'll do it in red now. So here we have 4 times, so carbon dioxide we have 4 times 2, or 8 oxygens. And with water we have 5 times 1, or 5 oxygens. This means we have 13 oxygens. So which means here we have 13 halves O2 molecules. So now this equation is balanced, but it's not balanced properly because what is a half of an oxygen molecule? So now what you can do is you can multiply the whole thing by 2. And multiply the whole thing by 2, and I'm going to go back to blue because I like blue. So 13, whole thing by 2, 13, 8, and 10. Okay, so let's count the number of each element. I'll start off with carbon. So with carbon, we have 8 on the left and 8 CO2s. That's the only one. We have 8 on the right. So I'll do I'll do pink for hydrogen. Hydrogen, we have 20 on the left, so 2 times the H10, 20 there, and we have 10 times 2 over here, or 20 on the right. And I'll go black for oxygen. Oxygen, we have 13 times 2, or 26 oxygens there. So 8 CO2s, 8 times 2 is 16, 10 times 1 is 10, or we have 26 oxygens on the right. So notice we have the same number of each type of atom on both sides of the equation. So that is how you balance chemical equations. The way you do that is you pick one atom and you balance it, and you just keep on going as an iterative process. Iterative means that once you get one, then you do it again and again and again until everything is solved. So.
Can I ask you to back up a little bit? Where did you get the 13 from?
Oh, 20, the 13? Okay. When I was balancing oxygens, I was, at the time, so going back in time, I had 4 CO2s and I had 5 H2Os. Okay, and 4 times 2, so 4 times 2 means 8 oxygens, and 5 times 1 means 5 oxygens. And 5 plus 8, so 5 plus 8 is 13 oxygens. And when you have an oxygen molecule, so oxygen molecule has 2 in them, so the fraction of oxygen molecules, O2 molecules, would be 13 halves, right? And since you can't have a half of a molecule, so remember discrete mathematics, whole numbers only, you have to multiply the whole thing by 2, and 1 times 2 is 2, 13 halves times 2 is 13, 4 times 2 is 8, 5 times 2 is 10.
Thank you.
Other questions? All right, let's see if you can solve this one. How many waters in this balanced chemical equation? So I want to know, what is this? How many waters, after you balance this chemical equation, I've highlighted in yellow the H2O. I want to know that coefficient. How many waters are in that balanced chemical equation? Okay, I'm going to go around and try to help you, but how many people think it's A? It's 6.5. How many think B, 13? How many think C, 26? How many think D, 24? So we got 2 students voting for 26, and the rest have no idea. Okay, I'm going to come around. Anybody stuck? Okay, all right. Go ahead and you can turn around and form your groups. Okay, so you do it one of two ways. I don't like doing the fraction way except for the very end. This one's the reverse. So because you have a number here, and an even number here, I'm gonna put double. Yeah. So now if you were to balance this, so you have so you have 12 carbons here, which means you have 12 carbons there. Right? So now, if you put the oxygens, you have 12 times 2 oxygens, so 24 plus 13, 24 plus 13 is 37, which means you have 12 times 2 is 24 and 13 so since you have here, so 2 is a package, Twix, okay. So if I want 37 Twix, how many packets do I need? I need 37 packets. this just makes it easier for multiplication. Yeah. I mean, the proper was 18 plus 18. That would be the proper way to go. 18 plus 1/2. No, when you multiply by 2, you do the whole thing. So you multiply the whole thing by 2. Times 4, this becomes 37. Are you guys following? It's so easy when I do. Odd number.
That was the thing.
Because there's 13 hydrogens.
But that was the first.
Yeah.
But we also
Yeah.
This 13 causes a problem with the oxygen.
Okay. So I told them 6.
I prefer whole numbers. So, but you could do the whole thing by fractions. You know.
All of this is your.
I mean, if you do the whole thing by fractions, this would be this whole 13 to start with, and 6.
First time I double checked.
12 plus 13 halves, so that would be 18.
So that was the first time.
That would be 18 halves of 2. Yeah. So then this would be 18.
I mean, that's the other thing, I guess. You have several different multiplication steps.
Yeah.
And they mix up when you start calculating. So like right now, I'm just going through the equation, so multiply this by 2, reading left to right. If I bring it to 6, this, my initial instinct is just multiply H2O like 2016 years. Go to 13 first, which got that on the original.
But that only happens when this is by 4, because there's 13 with 2 hydrogens. So here, 13 by 2 times 13.
Oh, right. Okay.
The details.
Yeah.
You double the details.
Which is why I really slow.
Well, if you like, I'm not a detail oriented person. I'm a very conceptual person. Like I practice leadership training, and I'm way over the top. Like this is I'm like a visionary. Like this is where we should be going.
Sounds like that's right up the alley of what we're doing.
Yeah. Well, I mean, you know. We're with me and my wife there, and then the
Do this.
you want me to.
Oh, she does everything. Hey, I want your pizza tonight. All right. You want to call? Two. Dodgy people.
But anyways, do you have any other questions or whatever? Check in again. Yes. No worries. by you start by doing each element, and you're on hydrogen.
You add
And
okay.
because this doesn't have any hydrogen. Yeah. Sure you can. Okay, now if you look at this, now if you look at the oxygen, so now when you go to the oxygens, you have 12 times 2, 24 oxygens here. You have 13 times 1, you have 13 oxygens here. So that means on this side of the equation, you have 37. You have 37 oxygens. Yeah, so you have 37 on this side, how do you do that? 37 halves. Or you multiply the whole thing by 2. Okay. Okay, so in red, I can't assume. In red here, this is so you're there, right? 12 CO2, 13 waters. 12 times 2 is 24 oxygens. 13 times 1 is 13 oxygens. 13 plus 24 is oxygen. Right? And 37. Yeah, it's, if you can tell the difference, my O's and zeros have fraction, right? Okay, so now, I just did this 37 and a half, or if you want, you can say 18.5. Either way, you have to have a whole number. So you multiply that again, the whole thing by 2 to get rid of that fraction. So then this becomes 4, 37. Yeah. Yeah. Wow.
But then wasn't my question how many waters you have on one side?
Yep. Yep. Welcome to chemistry. We do the elements. We do the element, one element. Yeah. But I mean, if you count the number of elements in each, I mean, once you balance the ratios, then you multiply 2, which is equivalent. Yeah. All right. So make sure I get it. Every problem.
Here.
Yeah.
The question I'm actually asking for, what you need when you do it. Second. That's fine. I was the moderator since 2017
I just need more examples.
Okay, well, in doing so, if you have questions, please let me know. All right, so I've gone around. It looks like everyone's kind of converging on it is 26. And to reiterate a few things, when you're doing this, it's all about the ratios. It's all about locking in the ratios, and you do it iteratively, meaning one at a time. So start off with balancing each element. So I'm going to start off with carbon. So there's 6 carbons in this molecule, which means we need to have 6 CO2s, because these 2 molecules on the left and on the right are the only ones that have carbon in them. So we know that the C6H13 has to be mean that there's going to be 6 CO2s. For every 1 unit of C6H13, there's going to be 6 CO2s. So then when you move on to hydrogens, so for hydrogens, there's 13 on the left and 2 on the right. So how do we get that to be 13? I usually do it by this way, 13 halves ratio. But now but that's an awkward ratio. So I multiply the whole thing. I'm changing colors. Multiply the whole thing by 2 and get 12, 13 like that. So now you are here, and you've locked in those ratios between C6H13, CO2, and H2O. Now we have to balance. Now we balance carbon and hydrogen. Now we need to balance the oxygen. And on the right side of the equation, we have 12 times 2, or 24 oxygens. And here we have 13 times 1. I'm getting the 1, it's like assuming it's right there. 13 times 1, or 13 oxygens. 24 plus 13 is 37, which means we have 37 halves ratio there of the O2s. So the half is awkward. So let's get rid of the awkward by multiplying the whole thing by 2. And you have 4, 37, 24, 26, like that. And now you have the set ratio, and each atom has there's the same number of each type of atom on both sides of the equation. So if you check 6 times 4, 24 carbons. 24 times 1, 24 carbons. Hydrogens, 4 times 13, so that's 26 times 2, that's 52. And 26 times 2, 52 here. And oxygens, so 37 O2, 37 times 2, that's going to be 74. And 24 times 2, that's 48, plus 26, and that is 74. Okay. Questions with that? Don't want to do math in front of people? Okay. All right. Now that let's go back a bit in time. What's in a Happy Meal? Here's your happy space. What's in a Happy Meal? Come on. I want a Happy Meal, guys. Fries. We got some fries.
Make you happy. It makes you sad.
Apples. Apple slices, I know. Anything else? What? Milk. And come on, why do you get Happy Meal besides the box that are creepy? The toy, yes, okay. And if I have 1,000 fries, 1,000 apples, 10 milks, and 1,000 toys, how many Happy Meals can I make? 10. But I got 1,000 toys. How come I can only make 10 Happy Meals? Milk, yes. I am limited. I am limited by something. I am limited by the milk. So I tell my boss and say, hey, I can only make 10 Happy Meals. He says, I'll tell you what. Here's another 10,000 toys. That will solve your problem. That's what they want anyways, the toys. Nope. Still can only make 10 Happy Meals, right? Because I would need to have, I'm limited by this. So the point with this, of course, is in chemistry, chemical reactions keep on progressing until they're limited by something. You give it enough time, the chemistry will just keep on going. It'll keep on reacting, until something runs out, right? When you go out at night and before, say you leave your credit cards at home and you want to go and eat as much as you can, you're going to keep on eating until you run out of money, right? That's your limiting reagent. So it makes sense. I mean, and chemical reactions happen the same way. So the happy meals are easy because they're all 1 to 1 to 1 to 1. How about something like ham sandwiches? Here's my very simple, boring ham sandwich where I have 2 pieces of bread and 1 slice of ham makes a ham sandwich. So if I have, oh, that's a highlighter. If I have 1,000 pieces of bread and 1,000 pieces of ham, how many ham sandwiches can I make with 1,000 of both reactants? 500. Then I will plus have 500 ham extra, right? So the difference now with the ham sandwich reaction is that we have a different ratio, different stoichiometric ratio. We need twice as much bread as we need ham. So in a chemical reaction, you can consume one reactant faster than the other. So, and that happens because of the ratios, just like making sandwiches. Make sense? So we're going to apply that, and this concept is called the limiting reagent. We're going to go up to talk about the limiting reagent, which we just did, and then we're going to get to something called theoretical yield. That's how much we can actually get of something. And then we're going to talk about the actual yield, which is what happens in real life. So real life, even in hypothetical chemistry class. So let's start with the first case of a limiting reagent. This is a limiting reagent problem. Actually, we talked about a limiting reagent last class. Driving your car. Driving your car is a limiting reagent problem. How far your car can go, you are limited by the fuel. You use oxygen too, but there's so much oxygen you don't even have to worry. You know what the limiting reagent is. So here, there's an example of one reagent in excess. So during photosynthesis, plants convert carbon dioxide and water into glucose by this reaction, this photosynthesis reaction. 6 carbon dioxides plus 6 waters with a photon from the sun forms 6 oxygens plus 6 glucose sugars. Suppose a particular plant consumes 37.8 grams of carbon dioxide in 1 week. Assuming there's more than enough water to react with all the CO2, what mass in glucose in grams can the plant synthesize from CO2? So let's talk about what this problem is and what it's looking for. What it's looking for, I'm going to highlight in yellow. Mass of glucose in grams. So this is what we need. We need mass of glucose in grams. And what information is given, I'll do this in blue, different color. We're given the equation and the amount of a reactant and enough water to do all that. So this 1 week thing, that's extra information. That doesn't matter. We don't care about how long it takes because the problem has given us other things. So what we need is in yellow, mass of glucose, and then given to us is what's in blue, highlighted in blue. So how do we solve this problem? We're going to use dimensional analysis, which means we're going to start over here with 37.8 grams of CO2. Start there on the left. Sorry, Mike. 37.8. So start with this on the left, and then we're going to get to the yellow portion, mass of glucose in grams, on the right. So if I've been training you correctly, the first thing you think of this, you're like, okay, how many moles is that? Hopefully that was the first thing that popped in your head, right? You have mass, that's awkward. So let's go moles CO2, and then if you do it, it's 44. 44 grams CO2. And I know it's 44.01, but 44 is good enough. So now we have mole CO2, and this is a new step. This new step is going to be moles. I'm just putting GLU for glucose to 6 moles CO2. This is a new step that you haven't seen before. And let me zoom in on this. So 1 mole of glucose needs 6 moles of CO2. I get this from the balanced chemical equation because over here on the right, the glucose, and this is, it's a 6 CO2 to 1 ratio between carbon dioxide and glucose. And I'm dividing it because we want to get rid of this unit here. So it's a new step. And also one that you need the balanced chemical equation to have. If you have an unbalanced chemical or an improperly balanced or unbalanced chemical equation, and you'll get the wrong answer. And then the next part is we need to go back to grams glucose. It's 180 grams glucose, grams CLU, 2 mole glucose. So now, notice we have exactly what we need. So the units cancel. Grams CO2 cancel, moles CO2 cancel, moles glucose cancel, and then we're left with grams glucose. And what is that? I'll go ahead and calculate it out. I could look in the book, but I'm feeling ambitious. 3.7.8 divided by 44 divided by 6 times 180 and equals 25. Okay. Let me sig figs 3. 25.8 grams glucose. And GLU is the shorthand for glucose. So if you do go on and study biochemistry or other biological classes, and if you see something that says GLU, so that's glucose. Glucose is our primary fuel for humans. Okay, so recap with this one. Here's the problem. Reading the problem, we've determined that the problem is asking for mass of glucose in grams. So we need to find mass of glucose in grams. And the given information that's important is that we start with 37.8 grams of carbon dioxide, and there's way too much water. So there's tons of water, and we don't have to worry about the water, that there's plenty of water, which means that our limiting reagents, so just like when we're making Happy Meals or making sandwiches, what we're limited by is the CO2. So limited by the CO2, and then how do we get to grams of glucose? Well, we convert to moles CO2, and then from the balanced equation, we figure out the ratio between carbon dioxide and glucose. It's 1 part glucose to 6 parts CO2, and then convert back to grams from moles, and we get 25.8 grams CO2 doing the dimensional analysis. Questions with this? Yes? CO2, so I don't have a periodic table handy. Carbon, it's 6, 12.01 on the periodic table. Oxygen is 8, 16.00. And for CO2, it's going to be 1 times 12.01 plus 2 times 16.00, and this equals 44.01. And I just didn't do the 44.0. Other questions? Okay. You're going, why would we care about doing this? We've done this quite a bit. This is, we've more or less abandoned this, but the idea of carbon credits. It was proposed back around 2007, 2008, the United States would have a $30 per ton carbon dioxide carbon tax carbon credit system. And there was tons of research to see what type of uptake you could get from crops and CO2. Al Gore, he wanted to do this with algae. He wanted to dump a bunch of iron in around Antarctica because the limiting reagent for algae is iron around Antarctica, and you can get an algal bloom from that, and then you can make a lot of money in carbon credits. Algae is also interesting. Algae is a very simple, it's a single-celled organism, and it grows very quickly. So compared to corn. So algae is a single cell, divide. Corn, to get a harvest from that, you have to plant the corn, then it grows roots, it grows a stalk, and then it grows the corn, and then you harvest the corn, and meanwhile, how long it took to get to the corn, though, had to grow the stalk, had to grow the leaves, had to grow the roots. Growing corn is very inefficient versus algae. And we're looking at algae for space travel. So if we're going to grow food, if we're going to make our own food on outer space, how we're going to do it? We're going to do it by algae, basically. And if you've read, gosh, who's the guy who wrote The Martian? He had another book about the moon, and they all ate algae on the moon. And we can genetically modify algae to put out proteins and fats, and we can tweak it so you get more. Like some algae will get more fat, some algae will get more carbohydrates, some algae get more protein. And so then we could. It's something we could do, at least for our macronutrients. We could get it all from algae, for sure. Be a very boring diet. In the book, it's called Artemis. Anthony Weir, that's his name. They called it gunk. So I remember that in the book. I guess it's like Soylent Green for the other thing. But that's people. So, but with algae and nutrients, though, there's a certain type of pollution called eutrophication. Eutrophication is when you add nutrients to the environment and then see what happens. So in the Mississippi River Valley, for instance, the limiting reagent for algae there is phosphorus. So and they found this out that when they had phosphates for detergents, you get algal blooms in the Mississippi River that would choke out the rest of the life. In the Gulf of Mexico, the limiting reagent is nitrogen. And this is a big deal when you have the spring runoffs, nitrogen fertilizers go into the Gulf of Mexico, and you get algal blooms from that. In and around Alaska, the limiting reagent there is sulfur. And every year with the change of seasons, the ocean currents change and sulfur comes up from the bottom of the ocean. The ocean's actually really shallow there. Sulfur comes up from the bottom of the ocean, and you have a huge algal bloom from the sulfur coming up. And then krill start to eat the plankton, and then we have our humpback whales. They migrate from Hawaii, and they go up and they eat the krill. So, I mean, not all eutrophication is bad. We have natural eutrophication as well. And also, with that in mind, algae is where we get our oxygen from. So somewhere around 3/4 of the oxygen of the Earth is still made by algae. So we think that we rule the planet. Algae. Algae are the rulers. We are subservient to them for our oxygen, and they've ruled the planet for a long, long time. Okay, so and when we did the calculations, like when we're doing the research on this, it turns out Europe was actually angry at the United States, because when we did the research in the United States, it turns out that our crops, our soil is so amazing here. Like, if you grow something in Iowa, Illinois, Indiana, or Ohio, it's just like, it's above and beyond anyone else. It's and we have Canada to thank for that. So with the more or less, we're in a period of interglacial. We're in a period called the Holocene right now. More or less, on average, there's 10,000 years of interglacial, which we're at now, and about 90-ish thousand years of ice age. And when the ice ages happen, the glaciers push all the topsoil off of Canada, and plop it right down over Ohio and the rest, and then retreats, lots of topsoil, plop, and after doing this 20, 30 times, now we've got lots of awesome topsoil in and around the Midwest and in the United States. And that's why we have so much freaking food right now. It's because of that. And our crops are just amazingly productive. And Europe's like, hey, we cannot use your numbers, United States. We cannot get the same productivity from our crops. So it's good to be in America, right? Okay. So let's move on a little bit. And this is, in fact, how we make ammonia. Hopefully this helps you see things a little better. So here, and we do this in iron, over iron. Nitrogen plus, so ammonia, and the ammonia is important because it's how we get fertilizer. So, fertilizer is the number 2 chemicals that we make. Can anyone guess what the number 1 chemical that we make in our industry is? Fuel. Fuel's number 1. Fertilizer's number 2. So, makes sense though, right? So, okay. Hydrogen gas is made by this, or ammonia is made by this way. The flask. So we start with this. This right here. We're starting with this, the ratio between hydrogen and nitrogen. What represents the reaction, and which one's the limiting reagent? So I guess you can see that. Hopefully you can see that. Let's count the hydrogens. So the hydrogens, 1, 2, 3, 4, 5, 6, right. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 H2s. And for N2s, we have 2. So, and let's, looking at this, that means we have a 1-to-3 ratio from this equation here. Look at the ratio between nitrogen and hydrogen. We have a 1-to-3 ratio. And so if hydrogen was the limiting reagent, 8, that means we would need 8/3 nitrogen, so it doesn't make any sense. If nitrogen is the limiting reagent with 2, that means we need 1-to-3, so 2 times 3, we need 6. We need 6 hydrogens to react all those nitrogens. So from that, nitrogen is the limiting reagent. And if all of them react, both of those 2 nitrogen molecules react, we will get 4 ammonias. Why? Because there's a 1 nitrogen to 2 ammonia. So if 2 react, we get 4 ammonias. And if we form 4 ammonias, that means we will have 2 hydrogens left over, because you need, so for every nitrogen, 3 is consumed. So for 2 nitrogens, 6 will be consumed. We start with 8. We have 8 minus 6, or 2 left over. And that's what this flask shows. So we've formed all the product, and we have excess reactants. So what about these other ones? Flask A, it hasn't been completed. The nitrogen did not react all the way, so it's incomplete reaction. B is correct as far as products, but it doesn't account for the excess reactants. So, questions with this? This is a question? 8. So 1 hydrogen, 2, 3, 4, 5, 6, 7, 8. Sorry.
I was looking at the equation. That's
Yeah. Sorry if I had to break out the old Sesame Street. So, other questions?
Sesame Street is good right now.
Oh, it is? Okay, good. It's still cool. I'm not completely disconnected. So, I mean, I'm a chemical engineer. I'm a PhD in chemistry, and chemical engineer too. One thing about chemistry class, sometimes the examples they give are completely just off the wall bonkers. What's nice about this one, this is actually how we do it. So this is how we make ammonia this way. We do it. It's usually liquid though, coming out. Well, I guess coming off the iron will be gas. You compress it down, and this is a big deal. If you look to the world's population, so around the end of, well, not last century, but the one before, 120 years ago, when we were approaching the year 1900, we had about 2 billion people on the Earth. And there was a problem. So what do we have right now? We have like an 8 and 9 or something? I don't know. So obviously something happened that we went from 2 billion to 8 billion plus in 100 years or so. I mean, that's a big change. That's 2 doublings of the population. That's huge growth, right? So obviously something happened around the year 1900 that we could have this huge population growth. And one of them was our industrialization of our agriculture. That was one of them. Can anyone guess what the other one is? There's 2 reasons. Antibiotics. So if you look at the reason why people died before 1920s, it was from illness. It was pneumonia, septicemia, and those type of things. So pneumonia was big, septicemia. So just whatever, you got an infection, eventually would kill you. And what kills us now? Heart disease and cancer. So heart disease, stroke, and cancer. It's a slow death, right? And people our age, it's accidents or murder. So, I mean, do people die from disease? Yes. Is it frequent? No. We have people that are making it through to reproductive age, and they're reproducing more, and there's more food. So we have lots and lots of people. And that's, the lack of food, that's called a specific, I think it's called a Malthusian catastrophe. There was a philosopher, his name was Thomas Malthus. He said, we've got a problem coming up. Food production is arithmetic, population is geometric. So arithmetic meaning, okay, so if I need to have, if I want to grow corn and I can get 40 bushels in an acre, how do I get more corn? I grow more corn. And if I have 40, if I plant 2 fields, I've got 80 now, and 3 fields, I got 120. And you look at population. So like my mother, her family, so she's one of 8, and I have 27 cousins on my mother's side, so 8, 27, and I have 4 siblings, so there's 5 of us, and there's 11 children, and I don't have any children, but there's 11 children in my immediate family, right? So you can see population can explode very rapidly, and that's called geometric growth. And especially since we're not dying anymore, we stick around, so populations are shoot up real fast. And around the year 1900, we got to the Malthusian catastrophe. We could not support the world's population by organic farming. So what we were doing, I guess it's still organic, we were mining nitrates in Chile. So guano and nitrates in Chile, and using that as fertilizer for crops. But mining is a limited resource. So there was an issue, like, okay, we need to find something to do. And what did we do? We made ammonia from hydrogen and air. Nitrogen from air, hydrogen from natural gas. And who figured it out was Germany. Germany figured it out, the BASF, the company that figured that out. And what happened after they figured it out? They invaded Prussia. So, yep. So ammonia, when you have ammonia, you can burn it to form nitrogen oxide. You can keep on burning it to form NO2. NO2 plus H2O makes HNO3, nitric acid. And so nitric acid you can use to make explosives. So does anybody know what TNT stands for? Trinitrotoluene. How do you make trinitrotoluene? You take toluene and you mix it with nitric acid. So dynamite. Dynamite is nitroglycerin. How do you make nitroglycerin? Nitric acid plus glycerin. So nitric acid, and there's even ammonium nitrate, that's a fertilizer bomb. So that's the Oklahoma City. So nitrates are explosive. They're also fertilizers. And so in this way, chemistry helped save the world, at least in terms of our population, which we've had uninhibited population growth since the 1920s because of ammonia synthesis. But we've also had some pretty big scale wars, right? So World War I was fought directly because of this. So in the what they found in Germany, and I don't know how he figured this. Karl Bosch figured this out. If you took iron from Sweden and you heat it up in the presence of hydrogen for 8 hours, you can make a catalyst that works. He was trying to do all these catalysts. It's called the Haber-Bosch process or Haber-Bosch process. He was using osmium. Osmium is more expensive than gold, so that's not viable on an industrial scale. So Karl Bosch figured out that iron from Sweden, heated for 8 hours in the presence of hydrogen, made a catalyst. So why did that work? Well, heating and hydrogen got rid of sulfur. Sulfur killed the reaction. Sweden specifically because it had potassium and aluminum in the ore. We didn't figure that out till 1970. So now we can make the catalyst we want. But if you know your history, Sweden was neutral in World War II. Why was Sweden neutral in World War II? Well, they brokered a deal with Hitler. Hitler wanted to invade them, and the reason why he wanted that is that he wanted the resources. But they brokered a deal that Sweden would supply Germany with iron ore to fund to make tanks and whatnot, and also for their ammonia synthesis. So that way they could continue to make explosives. So there's history. History is involved in chemistry, and there's political consequences of chemistry in history. So that's the kind of point of this. And it is important. So if you like the fact that we're all fighting obesity, at least, I worry about that. Because of good old chemistry and fertilizer. Simple as that. So, and well, I'll stop talking about that. I can talk for a long time. Okay, so this is not how we make ammonia, but ammonia can be synthesized. Ammonia can be synthesized by this reaction. 2 nitrogen monoxides plus 5 hydrogens makes 2 ammonias and 2 waters. Starting with 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen, what is the theoretical yield in ammonia in grams? So we have to figure out how much ammonia we can make from this. And unfortunately, this is a case where we don't have one. We have one excess, but it's not obvious. So in the previous example, talking about driving the car, it's the fuel that's the limiting reagent. For CO2 and algae, it's the CO2, not the water. There's too much water. So we don't know. We really don't know. So we have to do 2 problems. We have to figure out which one it is, and then we have to pick one. Do we pick the higher one, or do we pick the lower one? The lower one, yeah. You can't think too positively. We have to think which one are we limited by. Okay, so start off with both. 86.3 grams nitrogen monoxide, and I'll just put it in here, 25.6 grams of hydrogen. So we do the same thing, dimensional analysis, mole NO. So nitrogen is 14 plus 16 oxygen, that's 30 grams. 30 grams NO. So nitrogen is 14. If you look at the periodic table, it's 14. Oxygen is 16. 14 plus 16 is 30. And then we have to look at the ratio between nitrogen monoxide and ammonia. So 2 mole NH3 to 2 mole NO, and then 17 grams NH3, 2 mole NH3. So 17 because nitrogen is 14 plus 3 times hydrogen. 14 plus 3 is 17. Same thing for the bottom one. So this is mole hydrogen to 2 grams hydrogen. And there is a 2 mole ammonia to 5 moles hydrogen, 17 grams ammonia to mole ammonia. Okay, and the 2 to 5, so 2 NH3s to 5 H2s. And this step here, 2 to 2, or I just do 1 to 1, but I'm writing 2 to 2 because it's what's written on the chemical equation. So let me calculate this out. The book does it differently. They stop at moles, but I like doing just do the grams. 86.3 divided by 30 times 17, and this is equal to 48.9. And then that's small, huh? The next one, 25.6 divided by 2 times 17. Oh, geez. Oh. I screwed something up. 25 point. 6 divided by 2 times 5. Okay, that's a little better. Okay, this is grams. All right, so looking at nitrogen monoxide, we get 48.9 grams ammonia. Looking at hydrogen, we get 87 grams ammonia. And we have to pick the lowest one. We pick the nitrogen monoxide then. So the theoretical yield, meaning how much ammonia we can get from this, is 48.9. So because we looked at both, and it's not obvious, right? There's nothing to say like, oh, it's obviously one. But no, we don't know. So we have to calculate both. And the middle step is usually the hard one. It's the ratio in the balanced chemical equation. So, questions with this one? Okay. All right. Your turn. 100 grams oxygen, 100 grams hydrogen react. How much water will form? And I should balance the chemical equation for you. So 2 hydrogens plus an oxygen makes 2 waters. Hydrogen is 2 grams per mole. Oxygen is 32 grams per mole. So meaning you need to do 100 grams oxygen, 100 grams hydrogen, and then calculate both. Now, is anyone just completely stuck? I have no idea what's going on.
Yeah.
Okay. All right. So go ahead and start working. Where do you get stuck?
Well, before I forget, I'm going to ask you, where did you get 180 grams glucose from?
So C6H12O6
That's similar to the weight. And we did a previous example that calculated that.
Here? I'm sorry.
It was
Page 107.
I think we did that in class. I mean, you in the class, right? We did do it in class, but
Okay, see page 107. Okay.
but I
I
mean,
get the concept, but I just don't know what to do, how to get from point A to point B.
okay.
I get the concept.
Well, moles.
So you're trying to convert this. You got this from the periodic table,
Mhm.
and then
Well, I know it's nitrogen monoxide. It's 14 plus 60.
okay. So now here
Here from here, this, that.
2 moles A. Okay. And now here you're 17.
Yeah.
Is this
Same thing, but
the
it's
same thing that we did?
the formula mass, yeah. Yeah, same thing with glucose. So it's nitrogen is 14 plus 3 times 1 for hydrogen, so it's 17 grams.
Okay, and then when you multiplied all of this out, you
Okay, so 86.3 divided by 30, 2 over 2 is 1, times 17.
okay, so you divide this,
Yeah, bottom's divide, top is multiply.
and then okay, I'm sorry.
And 2 over 2 is 2 over 2 is 1.
Okay, 2 over 2 is 1.
Yeah.
So you divided that, and you're going to multiply this whole thing here,
Yeah. So multiplying by 1 gives you,
and then what do we do here?
you multiply by 17.
We multiply again.
Yeah.
So is it always going to be this way?
Yes.
We divide the first one, and then multiply the next two?
It depends on the numbers on the top and the bottom, right? The top number, the numerator is multiplication, the denominator is division.
Okay.
Like here, you multiply by 2 divided by 5.
Single nitrogen.
So moving on to this, I'm going to need to create this same kind
Yeah.
of thing
Mhm.
with each of these.
Yeah.
And I would need to go, do I need to figure anything out with these? Or?
Yeah, but I also give it to you. It's right here. 32. Let me do one for you. I'll do it for hydrogen. So for hydrogen, this is mole hydrogen, so 2 grams hydrogen, and 2 mole.
16 plus 20. H2.
That's my That's my shut up alarm. Class is over. We'll pick up here on Monday. It's Wednesday, right? Yeah, Monday.
And you use
Yeah.
the H2.
To see if I set this up right.
It's 32, not 2.
Oh, how'd you get 32?
16 times 2. So,
Oh, 16 what
yeah.
oxygen?
So oxygen is 16.
Right.
16 times 2 is 32.
Oh, okay. So this would be 32.
Yeah.
Okay, so now this would be 2 hydrogens as well.
2 grams. No, it'd be just 2 grams.
Oh, this is right.
Yes, that's correct. 2 grams is right.
But
This is 1 mole O2 to 2 moles H2O.
how come you tell me 1?
Because there's a 1 to 2 there.
Oh. 1, 2. Okay. And how do you find the last?
18. It's H2O 2 times hydrogen, 2 times 1 plus 16 is 18.
Okay.
And are you using this order for any other reason than that's the way it appears in the equation?
No, it's just because of the units. Because this one's going to be O2, that'll be moles O2, and then H2O. So it's not, yeah. It's the order doesn't come from the equation. This ratio comes from the equation, but the order is not.
2 moles H2O, 2 moles H2O. Okay.
We'll come
get
back.
there.
We'll come back. Are you in the lab?
Yeah.
Who's your teacher?
Peter Fisher.
Okay.
He's a little bit hard to follow. He makes you feel pretty stupid if you ask questions.
Oh. Hopefully I don't make you feel stupid. Okay.
You know, most of us in the lab really don't know what's going on.
No, I have to yield the room to Professor Irwin. Oh, where's Malachi? Guess it's there. 8. I just worry about him. He's a good student, but I don't want him to not pay attention.
Yeah.
Oh, hi, Mike. Are you taking biology? Oh, okay. Using your tuition waiver, huh?
Yeah.
You get 6?
Hopefully everything works out. I'll graduate in May.
What?